In this unit, we're going to be studying solutions, but in order to properly understand solutions, we need to understand why they form in the first place. So the ability of substances to disperse uniformly throughout another to form a solution, that depends on two factors. The first factor is the natural tendency of substances to mix. Now, the formation of solutions is favored by an increase in entropy. So substances naturally want to mix because that increases entropy, which is a measure of disorder, which we'll look at later this year. So the formation of solutions is actually a spontaneous process, unless molecules are restrained by either physical barriers, which we'll see in just one second, or by intermolecular forces, which is something that we'll look at throughout the rest of this lesson. So physical barriers, if you look at this example here, you've got oxygen and argon, and they're not mixing with one another because there's a clear physical barrier between these two gases. Now, if that barrier is removed, then these gases will spontaneously mix because that increases their entropy, their disorder. So it will spontaneously occur if that barrier does not exist. The second factor that affects the ability of substances to form solutions is the intermolecular interactions that are involved. Now, there are three different types of intermolecular interactions that we have to consider. The first one is solute-solute interactions. Now, this is the attraction of solute particles from one another. So, for example, when I have NaCl, sodium ions are attracted to chloride ions. So this is one type of solute-solute interaction. You can also have glucose, for example. So the attraction for glucose molecules for one another is a type of solute-solute interaction. Now, if you take that solute and you dissolve it into a solvent, the other type of interaction that must be overcome, that must be broken, is the solvent-solvent interaction. So, for example, if I'm dissolving it into water, water molecules are attracted to one another. And therefore, the attraction of water molecules for one another, that hydrogen bonding, that also has to be overcome. So you've got to put energy into breaking the solute-solute interaction and the solvent-solvent interaction. Now, that energy requirement is offset by the attraction of solvent and solute molecules for one another. So if that attraction is large enough, that will actually offset the energy that was required to break the solute-solute and the solvent-solvent interactions. Now, the solvent-solute interactions include four different types. There are dispersion interactions, which occur between nonpolar molecules. You have the typical dipole-dipole intermolecular attraction between polar molecules. You have hydrogen bonding, which occurs between polar molecules that have hydrogen and FO or N, so you can see that between ethanol and water. And then the ion-dipole interaction, which I just talked about. So, for example, sodium ions being attracted to water molecules. So these four interactions actually release energy when they are formed, while solute-solute and solvent-solvent interactions actually require energy in order to break those interactions. So solutions are going to be formed if the solvent-solute interaction is comparable in magnitude or greater than the solute-solute and the solvent-solvent interaction, because otherwise you're having to put more energy to break the solute-solute and the solvent-solvent interaction than you actually get from forming the solvent-solute interaction. And if that's the case, then the solution will not form. And so we'll look at examples of that in this video. Before we actually look at that, however, I wanted to come and discuss two terms that will be used. Here is sodium chloride being dissolved in water. So when a substance is being dissolved, we call that process solvation. So that's when solute particles are being surrounded by solvent particles. Now, specifically, if we're talking about water, that process is called hydration. So the solvation in which water is serving as the solvent. Let's now talk about the energetics of solution formation. I already hinted at this when I talked about whether or not a solution forms, but let's actually look at this. The enthalpy of solution, so the enthalpy that's involved in the formation of a solution, equals the sum of the enthalpy of the solute, so the energy required to break the solute-solute interactions, the enthalpy of solvent, so the solvent-solvent interactions, plus the enthalpy of mixture, so the attraction of solute and solvent for one another. So if you look at the diagram on the left-hand side, you see that the heat of solvent and the heat of solute, those are both positive, meaning it's an endothermic process requiring energy. Now, the enthalpy of mixture that occurs when a solute is attracted to a solvent, that is exothermic. So what this diagram on the left-hand side shows you is that since the enthalpy of solute plus the enthalpy of solvent is less than the enthalpy of mixture, then the heat of solution is actually going to be less than 0, meaning that it's an exothermic process. If the heat of solution is negative, if the process is exothermic, then that means that the mixture is going to be a spontaneous process. If you look on the right-hand side, the only difference is that the heat of mixture, the enthalpy of mixture, is actually less than it was before, which causes the enthalpy of solution to be larger than 0, which means that it is an endothermic reaction. So if it's slightly endothermic, then the process might still be spontaneous. However, if it's large enough, then the mixture will not be spontaneous. It will not occur because it requires too much energy to break the solute-solute interaction and the solvent-solvent interaction, and that is not made up by the enthalpy that is released by the attraction between the solute and the solvent. So let's talk about a couple of terms that are used to describe solutions. The first one is a saturated solution. So a common definition that you'll hear for saturated solutions is that they are solutions that contain the maximum amount of solute that can be dissolved into a solution. Now, why is that the case? What dictates the maximum amount? Well, if you have a high enough solute concentration, then that will increase the likelihood that solute particles will collide with the surface of the solid. And if they collide with the surface of the solid, they're going to crystallize, which is the opposite process of dissolving. So once you hit a certain concentration of solute, then the rate that the solute is dissolving is going to equal the rate that the dissolved particles are crystallizing. Now, once the rate of dissolving equals the rate of crystallization, you've reached what we call dynamic equilibrium, which we've already talked about. The rate of one process equals the rate of the opposite process. So at that point, no more solid can be dissolved, and therefore the solution is what we call saturated. So here's an example to show you. So for example, if you have enough of the solute particles dissolved, so for example, this is the sodium, this could be sodium chloride, once there are enough, then they are going to start interacting with the solid particle, causing them to crystallize, and therefore limiting how much solute can actually stay dissolved in the solution. Now we're going to be talking, when we're talking about solutions, we're going to be talking about this term solubility a lot, and the solubility is the maximum amount of solute that can dissolve in a given amount of solvent at a specific temperature. So when we're talking about an unsaturated solution, that solution contains less solute than is required to make it saturated. And when we're talking about a supersaturated solution, that actually contains more solute than it is required to make a saturated solution. So where solubility comes in here, if we take a saturated solution and we increase the temperature, as we'll see in the next video, that increases the solubility of that solute, so the amount that can actually be dissolved. So if we keep heating up the water and adding more solute, for example, then you're going to end up with more solute dissolved than was typically expected in a saturated solution. So one common example of this is rock candy. In rock candy, what you do is you take sugar water and you heat up the water and continue to add sugar to it. And then what you end up doing is allowing it to cool slowly, and it will form crystals. Now, it's not going to form crystals on which to crystallize and the impetus for crystallizing, and what causes the solute to crystallize as you cool the solution slowly is a seed. So a seed would just be, for example, in this case, a piece of sugar, so a couple of grains of sugar. If you add that, let's say, on a stick, so a stick covered in sugar, and you put that into a supersaturated solution as it cools, that provides the solute with the opportunity to crystallize, therefore forming the popular rock candy that you guys like to eat. In this section, I'm going to talk about factors that affect solubility. Now, this is just going to be the very beginning of talking about factors that affect solubility. In the next video, we're going to study this in detail. But just to continue on with our conversation about intermolecular attractions, the stronger the attraction between solute and solvent molecules, the greater the solubility of the solute in that solvent. So, for example, if we're talking about gases, if you look here, the solubility of gases increases as we move down this table. And the reason why, if you think about it, the attraction that's going to occur between gases and water, since these gases are nonpolar, is dispersion forces. So dispersion forces, the strength of dispersion forces, increases as you increase the size of the molecule. So as you move down this table, the size of these molecules actually increases, and therefore the solubility is going to increase along with it. So the attraction that's involved here is dispersion forces. Now, when we're looking at polar molecules in water, we're not going to be talking about dispersion forces. We're going to be talking about either dipole forces or hydrogen bonding. So in this case, if you look at these molecules here, the OH makes it an alcohol. The rest of these are just hydrocarbons. So as you move down this table, you keep the same OH, however you increase the number of hydrocarbons. So as you can see, the attraction between water and these polar compounds actually decreases as you move down this table. And the reason why is as you add hydrocarbons, the molecule becomes less and less polar and more nonpolar. So the attraction, the hydrogen bonding, is less important, and the more important attraction is dispersion forces, which are weaker than hydrogen bonding. So CH3OH has the highest solubility because the interaction between water and methanol is hydrogen bonding, which is extremely strong. Now, if you notice the solubility for C6H14 for these alcohols, it actually increases as you move down the table, and the reason why is because now the strength of intermolecular force that we're concerned with is increasing, that is dispersion forces, because these are nonpolar interactions. So just to review, the larger the alcohol is, the more it's going to act like a hydrocarbon. So for water, that's going to decrease solubility because the interaction that we're concerned with water for these are hydrogen bonds, while the solubility in C6H14 is going to increase because the strength of the dispersion forces increases. So when we're talking about solubility, you'll often hear the term or the phrase like dissolves like. So polar molecules dissolve polar molecules, and the reason why is that the attraction between the solute and the solvent molecules, the polar molecules, is strong enough that it overcomes the energy that was required to break the solute-solute interactions and the solvent-solvent interactions. Nonpolar molecules dissolve nonpolar molecules, again, because the dispersion forces that cause the attraction between solute and solvent molecules are comparable with those that were required to break the solute-solute and the solvent-solvent molecules. However, as you can see from this table, nonpolar molecules are not soluble in polar molecules, and the reason why is that the attraction between solute and solvent is not strong enough to overcome the attraction that had to be broken between solute-solute and solvent-solvent molecules. Now we have two terms to describe the solubility of solutions. The first one is miscible. So if a solution is miscible, that means that liquids are able to mix with one another. So if two solutions are miscible, they are able to mix with one another to form a homogeneous mixture. If solutions are immiscible, then they are unable to mix together. So keep in mind when we're talking about the ability of solutions to form mixtures with one another, what we're concerned with is comparing the enthalpy that's required to break apart solute-solute interactions and solvent-solvent interactions versus the energy that is released when solute and solvent interactions occur. So if they're comparable, or if the solute-solvent interaction is stronger, then the mixture will be formed. If they're not, however, such as what occurs with nonpolar and polar molecules, then the solution will not form, and those solutions will be immiscible.